Okay, let's make this a little bit less abstract and actually do some problems in projectile motion so you guys see how this two-dimensional kinematic equation thing works. Okay, so this is a true story. There's a frog named Rosie the Ribeter. Okay, if you guys could go to that slide. In the United States, the record holder for longest frog jump recorded at the famous Calaveras County Jumping Frog Jubilee that exists is Rosie the Ribeter. Hopefully you guys understand the little irony there. Who jumped 21 feet in 5.75 inches in 1986. If her jumping angle was 40 degrees, with what initial velocity did Rosie jump? Okay, cool. So you have little Rosie. So this is the Rosie problem. Okay, and you have Rosie starting here and doing a projectile motion jump from here over to here. Okay, and it tells you that distance is 21 feet and 5.75 inches. Okay, and first things first, you guys are probably going to be like, I want to convert that, right? And so I talked to Siri before this, and we had a heart-to-heart and converted this to 6.55 meters. You can tell me if me and Siri are wrong. Okay? All right. Now, we have everything that we need. Okay? We also know that, so this is the jumping velocity, right? This is what we're trying to find. This is our big question mark, right? And we know that the angle that she jumped was 40 degrees, okay? So the whole question is, if we know how far she jumped and we know the angle, can we find out what the actual velocity that she leapt off the ground with was, okay? For the record, guys, I just want to say that is incredible. That's almost the length of a classroom. Could you imagine if there's a frog on one side of the classroom leaping across the air and landing basically on the other side of the classroom? It'd be absurd and kind of freaky. It would freak me out. Okay, so first things first, we want to make laundry lists, right? Just like we did before, except now I'm going to make an X laundry list and I'm going to make a Y laundry list, okay? And so over here it's going to be VX1, VX2, AX, DX, and T, right? And over here I'm going to have VY1, VY2, AY, DY, and T. Okay, now the goal is just start filling in as much as we can possibly fill in. And you're going to realize that we can get a lot further along than we think we can, okay? Right now it looks like, oh, we only have like, 2 things here. You'd be surprised, okay? Let's start with V1x, okay? So here's our V, right? V1x then is going to be V cosine of 40, right? That our Vx initial is the original magnitude times the cosine of 40 degrees, right? But we also said that in the x direction, a is always 0, right? So we can go ahead and put 0 in there, which means that the velocity never changes, which means that Vx2 will be the same thing, V cosine of 40, right? And do we know dx? Sure do. That's the range, right? In projectile motion, the x distance you often call the range. So that's how far it's moved in x, which we have talked about is 6.55 meters, right? And so that begs the question then, what is time? Do we need to know time? We'll see. We'll see. But we don't know what it is right now. Okay, let's do the V1s, or the VYs. Vy1, well, we know that the y component of velocity is just going to be the same as this, but sine. So this is going to be V sine of 40, right? Your Vy2 is going to be, well, what did we say about the Vy component when it lands, when the guy lands, okay? Well, it has to be the negative of what it started out with, right? Because of symmetry, because of conservation of energy. So we put negative V sine of 40 there, okay? And what is our acceleration? Well, this is only under the influence of gravity, right? The frog, Rosie, is only under the influence of gravity the entire time, so that's going to be negative 9.8 meters per second squared. What is dy? Well, we start here and we end here, so there's no change in displacement, right? As far as the y dimension is going, so we just put a 0 there. So look at that. We basically filled in this entire situation, right? With just a few givens in the beginning. So that's neat. That's neat, right? There's a lot we can do in physics problems sometimes with a little bit of information. Okay, you will probably remember that after you have your laundry list, you need to then look at the kinematic equations, right? And so just to remind you guys, I'm going to write them right here. This is going to be crowded, but we have V2 equals V1 plus AT. Okay, we have V2 squared equals V1 squared plus 2AD. And we have D equals V1T plus 1/2 AT squared. Okay, so here's the thing. Cosine 40, that's just a number which we can put in our calculator. We'll worry about that then, okay? Those are just numbers. We want to solve for v's, right? Let's start looking over here in this guy, right? We don't have time, so that means the only equation that we could possibly use is this guy over here, right, to solve for our v's. But there's a problem, right? Because since V1 and V2 are the same, right, that's basically just giving you that 2AD equals 0, right? Velocities basically will cancel out, and you can't solve the problem, right? So that's not very helpful, right? But one thing that may be helpful, right, is this guy, right? So we can use this formula over for this dimension, right? If we pick this guy, we see that we have our V1, we have A, we just don't have T, right? So let me write that down really quick. So we have D equals V1T plus 1/2 AT squared, okay? A obviously is 0, so this goes away, right? And we know that D is just 6.55, right? And we know that V1 is V cosine of 40, right? So in other words, times T, right? In other words, if we can just find out what T is, we have everything and we can solve for V, all right? You guys are going to find out that in projectile motion problems, almost always the first thing you want to do is to solve for T in one dimension, because you can then use it in the other dimension to solve for whatever you're looking for. It's not 100% of the time, but I would say 90% of the time. So I would say first step for projectile motion problems, find the time if you can, okay? So the question is, can we find the time? Absolutely. We can use this first equation over here to solve for T, okay? So let's do that. V2 is negative V sine 40. Right? V1 is V sine 40. You guys may be tempted to cancel those, but they do not cancel, right? Because one's negative and one's positive. And then we have A, which is negative 9.8, times time, which is what we're solving for. Okay? Let's add this, subtract this over to the other side, right? So I would get negative 2V sine 40 equals negative 9.8 T, okay? Which means that T is just negative 2V sine 40 over negative 9.8. And I'm hoping I'm still in the screen, but just in case I'm not, so that you can follow me, it's negative 2V sine 40 over negative 9.8 equals T, okay? So now I can just go ahead and take this T and substitute it over there. I have two equations, two unknowns. This is why, the prerequisite for physics is algebra. You got to do some algebra, right? So if I rewrite this then, okay, I'm going to rewrite this. I have 6.55 equals V cosine 40 times negative 2V sine 40 all over 9.8. Okay, let's clean that up a little bit. There's two v's here, so this is v squared, right? So it would be 6.55 equals 2v squared cos 40. I'm going to erase this guy here, get this guy off. Cos 40 sine 40 over 9.8. All right. Cos 40 sine 40, you could just put in your calculator. Multiply both sides by 9.8, divide by 2, divide by cos 40, divide by sine 40. You get v squared. So you take the square root. And for the velocity of Rosie the Ribeter, I am getting 8.14 meters per second. Okay, so just solve this little equation here for v, and we should get 8.14 meters per second. All right. You can see, because of the two dimensions, it's a little bit messier and it's a little bit more involved, but I'll just run through the steps one more time really quick. You just make two laundry lists instead of one for each dimension. You can't mix and match. You got to keep the worlds separately, except for time, which is the same in both. Okay, and you then write your three kinematic equations, and within either dimension, you try to solve for what you can solve for. If you can't solve for something, then you find, another variable in another dimension to substitute in. In this case, it was time. In general, solve for time as a rule of thumb anyways. Just get it over with. And then substitute everything into your equations and solve for your final answer. And I'm going to pause here and start the future worked examples in another video so that you can go through this one as much as you want before moving on.